Okay, let's try this problem. Here they tell us that a 150-gram piece of copper at 95 degrees is placed inside an insulated container into 250 milliliters of water at 25 degrees Celsius. They want us to determine the final temperature once this combination comes to thermal equilibrium and reaches the same temperature. And they give us some information we need, including the specific heat capacities of the copper and water, as well as the density of water. All right, let's begin. So in this situation, we have a hot object, the copper, coming into contact with a cold object, the water. There is no reaction that occurs. We're simply going to transfer energy. Therefore, our beginning is always for a transfer of energy. Heat lost by the hot equals negative heat gained, well, in this case, by the cold water. So I'm going to go ahead and start by saying Q lost by the hot equals equal and opposite changes, heat gained by the cold. Okay, so who's losing hot? Hot copper. Who's gaining heat? The cold water. All right, now we just need to figure out how is that heat being transferred? Or is it causing a temperature change or is it causing a phase change? And then we go. So let's take a look at our hot copper. The copper starts off at 95 degrees. Once it hits the water at 25, all it's going to do is cool down. It goes through a temperature change. The way we calculate heat for a temperature change is MCAT. So we're going to go ahead and say MCAT of the copper, the hot copper, Cu, I'll call it, equals a negative. Now what about the water? The water's at 25 degrees. It's going to warm up, but it's not going to reach its boiling point. It's not going to go above the 95 degrees that the copper was. So all the water is doing is a temperature change as well. The way we calculate heat for temperature changes, MCAT again. So we're going to go ahead and say MC delta T, but in this case, we're talking about the water. All right, now we need to go ahead and put in our values. So let's start off by using the mass of our copper. The copper was 150.0 grams. The specific heat of the copper, they gave that to us. That was 0.385 joules per gram degrees C. The temperature change here, it's always final minus initial. So I'm going to say T final minus the initial temperature of that copper, which was at 95.0 degrees Celsius. Okay, that equals negative mass of the water. Well, in this case, they actually didn't give us a mass of a water. They gave us the volume of the water, 250 milliliters. However, they also gave us the density of water. They tell us that the density is a gram for every milliliter. So if we have 250 milliliters, well, then we're going to have 250 grams. I can prove that to you though. We could just do a really quick conversion. We can say over here, density, we could either convert it or use the density equals mass over volume formula. Your mass here is going to equal the density times the volume. The mass equals the density, 1 gram per mil, times your volume of 250 milliliters. Well, in this case, mils go away. We've got our 250 grams. Okay, so the volume is the same as the mass here. So let's go ahead and write in 250 grams. The specific heat of water, 4.184 joules per gram degrees C. And then finally, the temperature change of our water is T final minus that initial temperature, which happened to occur at 25 degrees Celsius. All right, we've got everything we need. Now we just need to simplify our math equation. A couple of things. I'm going to drop my units right now. It just gets a little clunky carrying my units through, and I'm going to take this step by step. The first thing I'm going to do is multiply 150 times 0.385. When I do that, I end up getting 57.8, and then I still have T final minus 95.0. That equals a negative. If we take the 250 times the 4.184, we end up getting negative 1046. And then we still have T final minus 25.0. Okay, next step. You could distribute both sides of the equation. You can absolutely do that. I think the numbers turn out a little prettier and it's a little less work if instead of distributing both sides, I'm going to divide both sides here by 57.8 right away. If I do that, that leaves this side of my equation really nice. All I'll have over here is T final minus 95.0 equals a negative. And if we do 1046 over 57.8, we have negative 18.1, and then we have T final minus 25.0. Okay, now all we need to do is distribute one time. So we're going to leave this side of the equation alone. T final minus 95.0 equals a negative 18.1 times TF is negative 18.1 T final. A negative times a negative, though, that's going to be a positive over here. 18.1 times 25 is 452.8. Okay, now I'm going to go ahead and combine like terms. I'm going to get my T finals over to this side of the equation. So 1 T final plus 18.1 T final is 19.1 T final. That equals, I'm going to bring the negative 95 over to this side of the equation. So 452.8 plus 95.0, that's going to go ahead and give you 547.8. And finally, last step, divide both sides by 19.1. We got to get T final by itself. And if we do that, we get a final temperature equal to 28.7 degrees Celsius. Now, you always want to do a double check and go, does this make sense? If an object at 25 degrees meets an object of 95 and achieves thermal equilibrium, well, that thermal equilibrium temperature has to be somewhere in between 25 and 95, right? Those are the extremes. The cold temperature is 25, the hot is 95, they're going to be in the middle. And this is definitely in between our two extreme temperatures right there, 28.7 degrees Celsius. Closer to the water because the water is not going to change temperature very much with its very high heat capacity. I hope that helps. Take care.